Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
Inside your phone, laptop, car, camera, smart TV, and even modern medical machines, there is a hidden city. Not a city made of concrete and steel, but a city made of silicon, metal, glass-like insulators, and billions of microscopic switches. A modern smartphone chip can contain more than 15 billion transistors, while advanced AI data center chips can contain hundreds of billions of transistors. These switches are so small that many of them are smaller than a virus, yet they turn on and off billions of times per second. But the real question is this: how do engineers build something so small, so accurate, and so complex, layer by layer, on a round piece of silicon? The answer lies in one of the most advanced manufacturing processes ever created: semiconductor fabrication. And at the heart of it is a technology that works almost like photography, but instead of printing pictures, it prints the future. This process is called photolithography. Before microchips, electronics were built using vacuum tubes, wires, and individual components. Machines were bulky, power-hungry, and unreliable. Then came the transistor. The transistor replaced large switching devices with a tiny electronic switch. But even with transistors, engineers faced a huge problem. Connecting thousands of individual components by hand was slow, expensive, and full of failure points. In 1958, Jack Kilby at Texas Instruments demonstrated one of the first working integrated circuits. Around the same period, Robert Noyce at Fairchild Semiconductor developed a silicon-based integrated circuit approach that became foundational for modern chips. In 1959, Gene Hoerney developed the planar process at Fairchild Semiconductor. This process used a flat silicon surface protected by silicon dioxide. This allowed transistors and interconnections to be built reliably on the same wafer. The Computer History Museum describes this as a revolution in semiconductor manufacturing. Instead of assembling electronics one component at a time, engineers could now manufacture entire circuits directly on silicon. That is the foundation of the modern semiconductor fab. Every chip begins with silicon. Silicon is chosen because it is a semiconductor, not a perfect conductor like copper, and not a perfect insulator like glass. It sits in between. With careful engineering, its conductivity can be controlled. The process begins with ultra-pure silicon. It is grown into a single crystal ingot, sliced into thin circular wafers, polished until the surface becomes mirror smooth, and cleaned to remove contamination. Modern advanced manufacturing commonly uses 300 mm wafers, about 12 inches in diameter. Wafer sizes increased from 50 mm in early production to 300 mm, helping reduce cost per chip. Imagine a perfectly polished silicon disc. It looks simple, but this round wafer will soon become the foundation for hundreds or thousands of chips. A chip is not carved in one step. It is built like a skyscraper, layer by layer, pattern by pattern, atom by atom. Before the wafer enters production, it enters one of the cleanest environments on Earth: the semiconductor cleanroom. Why? Because at nanometer scale, a tiny dust particle is not tiny. To a transistor, a dust particle is like a boulder falling onto a road. A single particle can destroy an entire circuit. Inside a fab, humans are not the main workers. Robots move wafers, machines expose patterns, sensors inspect surfaces. This is precision manufacturing at the edge of physics. The semiconductor process can be understood through one simple cycle: deposit, pattern, etch, dope, polish, inspect, repeat. Using a light-sensitive chemical called photoresist, engineers shine light through a mask to create a stencil. One layer becomes 2, 2 becomes 10, 10 becomes 50. Photolithography is the heart of chip making. It means writing patterns on a surface using light. A liquid photoresist is spread on the spinning wafer. Uniformity is critical. If it's too thick in one area, the pattern will not transfer correctly. Alignment is one of the most difficult tasks. If the new layer is shifted even slightly, the transistor may not work. In advanced chips, accuracy is measured in nanometers. The smaller the wavelength of light, the smaller the features that can be printed. This is why we moved from visible light to ultraviolet, and now extreme ultraviolet. To continue shrinking features, the industry moved toward EUV, extreme ultraviolet lithography. EUV light has a wavelength of 13.5 nanometers, almost in the X-ray range. To create EUV light, a CO2 laser fires at fast-moving droplets of tin. The tin becomes plasma, emitting 13.5 nanometers light up to 50,000 times per second. EUV is absorbed by almost everything, even air, so the system must operate in a high vacuum, using mirrors instead of lenses to guide the light. A chip has two worlds: front end, where transistors are created, and back end, where wiring connects them. A transistor is like a gate-controlled switch. As chips became smaller, we moved from planar to FinFETs, and now to nanosheets, where the gate surrounds the channel more completely for better control. Etching removes material from areas not protected by photoresist. Dry plasma etching is critical because it can create very vertical, nanometer-scale sidewalls. Through deposition, etching, and CMP polishing, we build the city. Then comes metallization, creating the microscopic wiring network that connects billions of transistors. Yield is everything. A small improvement in finding defects at the nanometer scale can save millions of dollars. Fabs are data-driven control systems. After all layers are complete, the wafer is electrically tested and cut into individual dies. These dies are packaged to protect them and connect them to the outside world. Semiconductor fabrication is engineering at the limit of physics. A fab must control nanometer dimensions, atomic films, and high-vacuum environments repeatedly. The next chapter is beginning with high-NA, EUV, and nanosheet transistors, but the fundamental cycle remains: build, pattern, remove, repeat. A chip is one of the greatest achievements of modern engineering. It transforms sand into a microscopic city of logic. The world runs on chips, and chips are built by light. This is semiconductor fabrication, where engineering writes the future, 1 nanometer at a time.